Body. In my previous class, we were discussing what is called hyperconjugation. There we have seen one of the hydrogen atom from alpha carbon atom is in conjugation with the unsaturated system. That means this sigma electron, which is single bond electron, moves for a new double bond, and this double bond is polarized. I have already written, just I am revising little bit. What you can see, this is the functional group. The first carbon atom attached to it is called alpha carbon atom, and the hydrogen atoms attached to it alpha hydrogen atom. So you can see there is no bond between the alpha carbon atom and one of its hydrogen atom. Therefore, hyperconjugation is sometimes called is no bond resonance. Also, in my previous class, I have told you, more the number of alpha hydrogen atom, more is the number of hyperconjugated structures, and hence more is the stability. And I have given you examples. Now, sometimes question asks, the methyl group which does not contain any excess of electron, how it is capable of pushing electrons when it is, say, here I have attached to an unsaturated conjugated system, that is benzene. Here one of its alpha hydrogen atom, carbon hydrogen bond, sigma bond electron is gives you can see one of its sigma bond electrons forms a new carbon hydrogen bond. Double bond is there, so one of the sigma electron is being in conjugation with the pi electron system, that is with conjugated system of benzene. One also you can write this electron may be involved. Or also the sigma electron from carbon hydrogen bond is in conjugation with the pi electron system. So, due to contribution of these structures we have written, the methyl group, if does not possess any excess of electron, it is capable of pushing electrons. So you can find there is a no bond between one of its hydrogen atom and carbon atom, therefore it is called no bond resonance. Next I shall proceed to bond fission, bond breaking, bond fission. Bond fission means bond breaking. It can be in organic compounds. Bond breaking may take place by two different ways. Bit one, homolytic fission. Here the shared pair of electrons, say between the two atom A and B, are equally divided. That means due to homolytic fission, each atom, say A and B, they retain their own electron. These are called free radicals. So, homolytic fission results in the formation of free radical. In free radicals, each carbon atom undergo sp2 hybridization. The second way is your heterolytic fission. During heterolytic fission, the shared pair of electron is retained by one of the atoms only. Say for example, if you take carbon X bond, there can be two probability during a heterolytic fission. If X retains the shared pair of electron, then carbon becomes positive charge. This is called carbocation or carbonium. Here carbon undergo sp2 hybridization. The second probability, say carbon may retain electrons. Heterolytic fission, that is unequal division. Here carbon retains the electron, become negative charge, called carbanion or carbanium. Here carbon undergo sp3 hybridization. So bond breaking in organic compound may take place by two different ways. In one is homolytic fission, which results in the formation of free radical. There each contributing atom retains their own electron. During heterolytic fission, which results in the formation of either carbocation or carbonium or carbanion or carbanium. Here one of the atoms retain the entire shared pair of electron. Next is attacking reagent. The reagent which attacks or by which a reaction starts are called attacking reagents. These are of two types. Electrophile. Phile means loving or liking. So electrophiles means they are electron loving, are either positively charged ions, or if neutral molecule, that means molecules having deficiency in electrons. So they attack a place, attack means react place where there is more electron density. So electrophile may be two types, either they are positively charged ions or neutral molecules having deficiency in electron, and they attack a place, attack means react a place where there is more electron density. I am giving examples. Bit 1, positively charged electrophiles. They can be H plus or say H3 plus hydronium ion, Br plus, Cl plus, aku kanti bromium, chlorium ion, etc. These are the positively charged electrophiles. The neutral electrophiles, neutral electrophiles, the molecule which contain less amount of deficiency in aluminum chloride, boron trifluoride, ferric chloride, sulfur dioxide, sulfur trioxide, etc. So, electrophiles are either positively charged ion or neutral molecule having deficiency in electron will attack a place where there is more electron density. Next is nucleophiles. Nucleus is positive charge. Nucleophiles means which attack a place where there is less electron density. So, nucleophiles is either negatively charged ions or molecules or neutral molecules having excess of electron, and will attack a place. Attack means react. Attack a place where there is less electron density. So, like electrophiles, nucleophiles are of two types, that is negatively charged nucleophiles. Here it can be OH minus, say Cl minus, bromide minus, Cn minus, etc. Or they can be neutral molecules but having excess of electrons, that is neutral nucleophiles. They have excess of electron, like water, lone pair of electron there, alcohol, ammonia, or say amines, they have got excess of electron. So, attacking reagents are of two types. One is electrophile, another is nucleophile. The last one is type of reaction. In organic reactions, types of reactions. 4 important reactions are important. Is number 1 is your addition reactions. Here 2 molecules are combined to form a single compound. Say ethene, when treated with bromine, form. This is your 1,2 dibromoethane. This type of reaction is exhibited by unsaturated compounds, that is addition. Now, the second one is substitution reaction. Substitution means one of the atoms or group is replaced by another atom or group. During substitution reaction, one atom or a group is replaced by another atom or group. Say methane, when treated with chlorine in presence of say diffused sunlight, one of its hydrogen atom is replaced by chlorine, gives you chloromethane. So, this is a substitution reaction. This reaction is exhibited by saturated compound. One of the atoms or groups is replaced by another atom or group. The third reaction, which are mostly occur in organic reactions, is your elimination reaction. Elimination reaction. Here small molecules are eliminated. Say if we take bromoethane. Bromoethane, when treated with alcoholic potassium hydroxide, means potassium hydroxide dissolved in alcohol. Here HBr, one hydrogen from here, bromine replaced, giving ethylene or ethene. HBr and potassium hydroxide again react to form potassium, because acid base react to form salt and water. This is called elimination reaction. And another reaction is rearrangement reaction. Here one atom or group is migrated from one part to another part within the same molecule. Say if we take, say, vinyl alcohol, vinyl alcohol. Here one hydrogen atom migrates from oxygen to carbon. This undergo rearrangement reaction to give you acetaldehyde. So these are the four important reactions which mostly occur in most of the organic reaction, in addition to sometimes oxidation reduction also. So this is all about fundamental concepts in organic reaction mechanism. Next I am proceeding to isomerism. So isomerism word has been derived from two Greek words. Iso means same, mers means sparse. Here compounds having same molecular formula but different arrangement of atoms or groups. That means they differ in the arrangement of atoms or groups, and they possess different physical and chemical properties, are called isomers. Remember, compounds are called isomers, and this phenomenon, this word phenomenon I will frequently use, is called isomerism. These are of two types. One is structural isomerism, another is stereo isomerism. Now, so far structural isomerism is concerned, compounds have same molecular formula but having different structures due to different arrangement of groups or atoms are called structural isomerism. There are 5 types. One is called chain isomerism. Second is your position isomerism. Third, functional isomerism. Fourth, metamerism. And the last one under this is tautomerism. So, in structural isomers, compounds have same molecular formula but different structures. Phenomenon will be known as structural isomerism. There are 5 types: chain isomerism, position isomerism, functional isomerism, metamerism, and tautomerism. Let us discuss chain isomerism. Here compounds have same molecular formula but they differ in their carbon chain. They differ in their carbon chain. If we take this compound, this is your pentane. It is a straight chain compound, straight chain. Here you can write another compound having same molecular formula, that is your 2-methyl butane. Another compound having same molecular formula, but chain is different. This is your 2,2-dimethyl propane. First one is straight chain, second one has got one branch, third one has got two branches. So chain is different. They have got same molecular formula, that is it has got C5H12. In all cases same, but they differ in their carbon chains. Therefore they are called chain isomers, and the phenomenon is called chain isomerism. Chain isomerism. Next is position isomerism. Here the compounds have same molecular formula, same functional group is also same, but the position of the functional group is different. They are related to each other as position isomers. Phenomenon will call it position isomerism. So here molecular formula same, functional group same. This is your 1-propanol, functional group OH group, and it contains 3 carbon atom, 8 hydrogen atom, and same you can find the same molecular formula, same functional group is your 2-propanol. Similarly, if we take but1-ene and but2-ene, they have got same molecular formula, same functional group, here also carbon-carbon double bond, but position of the double bond is different. They are called position isomers. Phenomenon will be known as position isomerism. Third one is functional isomerism. Here compounds have same molecular formula, but altogether different functional group. Functional group will be different. Say for example, your ethyl alcohol or ethanol and ether, say methoxy methane. So you see they have got same molecular formula, that is C2H6O, but altogether different functional group. One is alcohol, another is ether. So you remember, alcohol and ether are functional isomers of each other. Similarly, between aldehyde and ketone, if we take aldehyde, propanol, and having same molecular formula, your propanone ketone, they have got 3 carbon atom, 6 hydrogen atom, and 1 oxygen atom. So aldehyde and ketone, they are functional isomers of each other. Functional group is different. One is aldehyde, another is ketone. Another example you can take, say acid, propanoic acid and an ester. This is your methyl ethanoate. They have got same molecular formula. It contains 3 carbon atom, 6 hydrogen atom and 2 oxygen atom. So acid and ester, they are functional isomers of each other. So in these cases, what we have found, they have got same molecular formula but altogether different functional groups known as functional isomers. Phenomenon will be functional isomerism. Fourth one is your metamerism. Here compound also contains same molecular formula, same and same functional group. They have got same molecular formula, same functional group, but they differ in the number of carbon atoms in either side of the functional group. Number of carbon atom on either side of the functional group is different. So the functional group will remain in the middle. You will take this compound, altogether 5 carbon atom, and so also here this compound is 1-methoxy butane. Second one is 1-ethoxy propane. So they differ in the number of carbon atom on either side of the functional group. Another example you can take, say secondary amine. And where the functional group remain in the middle. So altogether here 5 plus 1, 6 carbon atom, they are 4 plus 2. So number of carbon atom remains same, so molecular formula will be same. Functional group be same, both cases secondary amine, but in the alkyl groups present on either side of the carbon atoms are different. This is your N-methyl pentane 1-amine. This is your N-ethyl butane 1-amine. So in so far the metamers are concerned, they have got same molecular formula, same functional group, but the number of carbon atom on either side of the functional group is different. Related to each other as metamers, phenomenon will be metamerism. And the last one so far the structural isomerism is concerned is your tautomerism. Tautomerism. This is a special case of functional isomerism. Here the functional group will differ. Two compounds having different functional group but existing in dynamic equilibrium are called tautomers. Phenomenon will be known as tautomerism. That means here the compounds have same molecular formula but different functional groups, but these two different compounds exist in dynamic equilibrium, means one form can be converted to another form. It is called tautomers phenomenon is called tautomerism. Say methyl cyanide, it is shown by double arrow equilibrium, and isocyanide, there is a coordinate bound from nitrogen to carbon. This is your methyl isocyanide. Another example you can take, say vinyl alcohol. Vinyl alcohol is in dynamic equilibrium with acetaldehyde. You can find they have got same molecular formula but different functional group. Another you can write, this is, and this is common name is acetoacetic ester. This is called keto form of acetoacetic ester. This is called annual form of acetoacetic ester. So one form can be converted to another. They are in dynamic equilibrium state. They have got same molecular formula but different functional group. And one form can be converted to another, that is called they are in dynamic equilibrium forms. So this is all about structural isomerism. It is compounds having same molecular formula but different structures related to each other. A structural isomer phenomenon is called structural isomerism. 5 types: chain isomerism, position isomerism, functional isomerism, metamerism, and tautomerism. Next is stereo isomerism. Here compounds have same molecular formula but they differ in the arrangement of atoms or groups within the molecule, are known as stereoisomers. Phenomenon will be stereoisomerism. Again, these are the 2 types. One is configurational isomerism and second was conformational isomerism. Configurational isomerism, again 2 types. One is called geometrical isomerism and second one is optical isomerism. So stereoisomerism, there are stereo word comes from space. So from space stereo word has come. So compounds having same molecular formula but differing in the arrangement of atoms or groups around or within the molecules by which they have different physical and chemical properties are called stereoisomers. Phenomenon will be known as stereoisomerism. 2 types: configurational isomerism, conformational isomerism. Configurational is again 2 types: geometrical isomerism and optical isomerism. So I am going to discuss one by one. That is geometrical isomerism. Now, in geometrical isomerism, compounds have same molecular formula, but they differ in the arrangement of atoms or groups around carbon-carbon double bond or carbon-nitrogen double bond. That means compound having same molecular formula but differing in the arrangement of atoms or groups around a carbon-carbon double bond or carbon-nitrogen double bond are called geometrical isomers. Phenomenon will be known as geometrical isomerism. Here, this arises due to restriction of free rotation. Restriction of free rotation around carbon-carbon double bond or carbon-nitrogen double bond. So, by which this leads to different geometry of the compound, hence the name is geometrical isomerism. That means compound having same molecular formula but differ in their arrangement of atoms or groups around carbon-carbon double bond or carbon-nitrogen double bond are called geometrical isomers. Phenomenon will be known as geometrical isomerism. So, there is a restriction of free rotation around carbon-carbon double bond or carbon-nitrogen double bond. So, requirements when the compound will be exhibit the geometrical isomers. So, first requirement, it must contain a carbon-carbon double bond or carbon-nitrogen double bond. This is most important. The first requirement is it must contain a carbon-carbon double bond or carbon-nitrogen. But all the compounds containing carbon-carbon double bond or carbon-nitrogen double bond will not exhibit geometrical isomerism. The second condition they should satisfy. That means the atoms or groups attached to carbon atom or atoms having double bond must be different. This is most important. First requirement, they should contain carbon-carbon double bond or carbon-nitrogen double bond. The second is most important. The atoms or groups attached to carbon atom or atoms, in case of carbon-carbon double bond, there are two carbon atoms having double bond must be different. If they are equal, it cannot exhibit geometrical isomerism, though it contains say carbon-carbon double bond or carbon-nitrogen example. For example, propene. This I have written this formula CH3 CH double bond CH2. Here you can find two hydrogen atoms are same. You can, by differing, you must thinking this will be another structure. No. These are the same geometry. Here two hydrogen atom on the same side of carbon-carbon double bond, methyl and hydrogen on the other side. So also there. So these are not geometrical isomers. Similarly, but1ene, but1ene, you can find though it contain the carbon-carbon double bond, and you may think that these are the two geometrical forms, but no, they are the same form. Why? Because you can find two hydrogen atoms are on the same side of carbon-carbon double bond. Here also ethyl group hydrogen are on the same side. So also here ethyl group and hydrogen are on the same side. So it will not exhibit geometrical isomerism. These are not geometrical isomers. They have got the same structures, though it contains carbon-carbon double bond. So propene, but1ene, though possess carbon-carbon double bond, but will not exhibit geometrical isomerism. On the other hand, you take but2ene, but2ene here, and another form which you can write is here. You can see here two methyl groups are on the same side of the carbon-carbon double bond. In the second case, they are on the opposite side. So these are the two different geometry of but 2En. If the same group or same functional group or like groups are on the same side of carbon-carbon double bond, it is called cis form. So this is cis form of but 2En. Here two methyl group are on the same side, here two methyl group are on the opposite side, is called trans-double transform of but 2En. Similarly, so here but 2Ne will exhibit geometrical isomerism. I have written there, one is cis form, another is transform. Similarly, here also find two chlorine atoms are on the same side of the carbon-carbon double bond, but here the opposite side. So first one will be cis form of compound name is 1,2-dichloroethene. So here it is trans because two chlorine atom opposite to carbon-carbon double bond, transform of 1,2-dichloroethene. Another example I can also write, say carboxyl group is there. Here two carboxyl group are on the same side, and another you can write two carboxyl group may be opposite side of carbon-carbon double bond. So this is your cis form of your but 2ene dioic acid. This is your trans form of but 2ene dioic acid. Most of the time we use their common name, in sometimes here it is called maleic acid, and this one is your fumaric acid. So if there is a carbon-carbon double bond, two like atoms or like groups are on the same side of the carbon-carbon double bond, it is called cis form of the compound. If they are on the opposite side, we call it trans form of the same compound. Now, if there is a carbon-nitrogen double bond, mostly in oximes, there can be two types. If it is obtained from aldehyde, it is called aldoxime. If it is obtained from ketone, it is called ketoxime. Their name is a bit different. If hydrogen and OH group here they are, if they are on the same side of the carbon-nitrogen double bond, or there can be another probability opposite side. This is called syn form of compound name is benzaldeoxime. Oxime is a class where there is carbon-nitrogen double bond. This is called antiform of benzaldeoxime. So if hydrogen and hydroxide group are on the same side of carbon-nitrogen double bond of aldoxime, then it is called syn form. If they are on the opposite side of carbon-nitrogen double bond, it is called antiform. In case of ketoxime, same syn and anti word also being used, but there are two alkyl group or which are different. Here I have taken one alkyl group and another group. Now here the compound named as methylphenyl ketoxim. The group which you are pronouncing first, that is methyl, because alphabetical order it is being pronounced, M comes before P, so it is methylphenyl ketoxim. Since they are on the same side, this is called syn form of methylphenyl ketoxim. Here they are in the opposite side of the carbon nitrogen double bond. This is called antiform of methylphenyl ketoxim. So, two types of word are being used in geometrical isomerism. If there is carbon-carbon double bond, two like groups or atoms are on the same side, we use cis. Opposite side, we use the word trans. So far oxim are concerned, maybe two types, for aldoxim and ketoxim, we use the word syn and anti. In case of aldoxim, if hydrogen and hydroxide on the same side of carbon-nitrogen double bond, it is called syn form, opposite side anti form. In case of ketoxim, the group which we are pronouncing first and the OH group, if they are on the same side of carbon-nitrogen double bond, it is called syn form, or if they are opposite side of carbon-nitrogen double bond, it is called anti form. Now, so far the properties of geometrical isomers are concerned. Properties, they have different physical properties. But say they have same chemical properties. Why? Because the functional groups are same, except the rate or the speed of the reaction is different. Speed is different, but the reaction will be same. Physical property, they have got different physical properties. Now, if we take say maleic acid, it's a common name I am writing, maleic acid. Here you can find two carboxyl groups are on the same side. So if we heat it, it will lose one molecule of water, and you will get the corresponding anhydride easily. Corresponding anhydride, maleic anhydride is obtained easily, because two functional groups are on the same side of the carbon-carbon double bond. On the other hand, if we are taking fumaric acid, here the two carboxyl group are on the opposite side of carbon-carbon double bond. So, formation of anhydride will take time. Will take time to form its anhydride. So, in first case, reaction is faster than in the second case. So, they will have some chemical properties, but speed or the rate of reaction is different, but they have got different physical properties. This is all about geometrical isomerism. Next is optical isomerism. Now, so far the optical isomers are concerned, they have got same molecular formula, even same functional groups, same physical chemical properties also, but they differ in their behavior, towards, most important one is polarized light. I will tell you what is polarized light. So, optical isomers, they have got same molecular formula, same physical and chemical properties, only they differ in their behavior towards polarized light are called optical isomers. The phenomenon will be known as optical isomerism. Now, when light passes through a medium, the particle of the medium can vibrate in infinite possible plane. This is called ordinary light. All these planes are perpendicular to the line of propagation. When ordinary light is passed through a particular type of prism called Nichols prism, all the possible planes are being cut up. Light is only vibrate or allowed to vibrate only in one possible plane. This is called polarized light. So this is a uniplanar vibration of the particle of the medium, perpendicular to the line of propagation, only one plane, is called polarized light. If an organic compound, either in liquid state or in solution state, which should be transparent to light, you can't take solid. If solid, you will have to take a solution through which light can pass, or you can take it in liquid state. No gaseous molecule taken here. So this is transparent to light. If organic compound is kept in the path of polarized light, two things can happen. This organic compound is not capable of rotating the plane of polarized light. The plane is not changed. Its original plane, if you see here, remains same. Then the organic compound is said to be optically inactive. It is not capable of rotating the plane of polarized light. The second thing, organic compound is capable of rotating the plane of polarized light. It can rotate. Then it is said to be optically active. So there is a plane here. If you can see as such x dash plane, the organic compound is not capable of rotating the plane of polarized light. That was optically inactive. If rotated, there can be two things. It can either rotate to, say, y dash plane, or it can rotate to, say, z dash plane. There can be two times. If optically active, then it can be two types. The plane is rotated from, say, x dash plane to y dash plane. That means clockwise, or towards your right, clockwise rotation. Then the organic compound is said to be dextro-rotatory form, or simply write D form. Organic compound is capable of rotating the plane of polarized light from its original plane, say x dash, to new plane y dash, then when clockwise or towards the right. It is called dextro-rotatory form or D form. The second case, original plane, say x dash, is rotated to z dash plane, or anti-clockwise direction, or towards your left, you can see. Then it is called levo-rotatory form or L form. So, organic compound which are capable of rotating the plane of polarized light can be of two types. It can rotate from x dash plane to y dash plane, clockwise direction or towards the right. Then the organic compound said to be dextro-rotatory form or D form, or It can rotate the original plane x dash to z dash plane anticlockwise direction towards the left, called levorotatory or L form. So, ordinary light, they are the particle of the medium, can vibrate in infinite possible planes. When it passes through a particular type of prism, Nichols prism, all possible plane vibration are being cut up. It is allowed to vibrate only in one possible plane, that is called polarized light. If an organic compound is kept in its path, there can be two things. Organic compound is not capable of rotating the plane of polarized light, then it is called optically inactive form. If it is capable of rotating the plane of polarized light, it is called optically active form. It can be two types, either clockwise direction it can rotate or anti-clockwise. If clockwise, it is called dextrorotatory or D form. If anti-clockwise, it is called levorotatory or L form. When an organic compound becomes optically active, requirements: number one, it must contain one or more asymmetric or called chiral carbon atom. What is asymmetric carbon atom? Now, asymmetric chiral carbon atom or chiral. Asymmetric or chiral carbon atom is one whose four valencies, carbon you know, they have got four valency, tetravalency, four valency of the carbon is satisfied by four different atoms or groups. If four different atoms or groups are attached to the carbon atom, that means all the valency of the carbon, that is four valency, satisfied by four different atoms or groups, it is called asymmetric or chiral carbon atom. I am giving one example. If we take, say, propanoic acid, it does not contain any asymmetric carbon atom. This is your propanoic acid. So, it is optically inactive. It will not rotate the plane of polarized light. But if one of its hydrogen is replaced by, say, hydroxy group. So, this carbon atom which I am marking as a star 1, a star mark carbon atom, you can call it here, four valence of it are satisfied by four different atoms or groups, one methyl group, one hydroxy, one carboxyl group, one hydrogen. This is your 2-hydroxy propanoic acid. Common name is lactic acid. This will be optically active since it contains the star mark carbon, that is your asymmetric carbon atom. The number of isomers will be, or number of isomers depends upon how many asymmetric carbon atom it contains, 2 to the power n, where n is asymmetric carbon atom. If we contain one asymmetric carbon atom, 2 to the power 1 will be 2. If contain 2 asymmetric carbon atom, 2 to the power 2 will be 4. If contain 3 asymmetric carbon atom, 2 to the power 3 will be 8, and so on. So, it must contain one or more asymmetric carbon atom. The second requirement is compound should be an unsymmetrical one. Unsymmetrical one, that is, it should not possess plane of symmetry. If it possesses plane of symmetry, it will be optically inactive. Say for example, ball, it has a plane of symmetry. But if we take a tree, it does not possess any plane of symmetry. This compound possesses plane of symmetry, plane of symmetry. Similarly, any organic compound having plane of symmetry will be optically inactive, but having no plane of symmetry will be optically active. This is the first requirement. The compound must possess one or more asymmetric carbon atom. And second, I have told you it should be an asymmetric one. If we mix D form and L form of a particular compound in equimolar proportion, means equal amount, in equimolar proportion, then it will be an optically inactive, because suppose D form rotate clockwise, same amount rotated by L form, it will be optically inactive form, and this mixture is called racemic mixture. So racemic mixture is optically inactive mixture due to equimolar proportion of D form and L form. D form and L form. So due to externally compensation, racemic mixture become optically inactive. This is all about optical isomerism. Next I am going to conformational isomerism. This arises due to free rotation. Once I have used the term restriction of free rotation in geometrical isomerism, here there is free rotation around a carbon-carbon single bond. When there is a single bond, there is free rotation. You can find infinite numbers of conformations. All these isomers are called conformations, infinite possibles, or conformational isomers. Phenomenon is called conformational isomerism. I am giving only one example. Say for example, if we take ethane, CH3, and there is another carbon atom behind it. So, if this is a carbon-carbon single bond, this carbon atom I have taken to the front, this is in the back. If you look to this hydrogen atom, you can't see this one. This is obstacle. Similarly, if you see this hydrogen, you cannot see one. This will be obstacle. So this is called eclipsed form. Eclipsed form of ethane. If keeping the first carbon atom, front carbon atom constant, if you rotate it, the second carbon to throw an angle of 60 degree, the configuration of the first carbon atom remains same. Here hydrogen, 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 and this is called staggered form. Staggered form. So it is rotated through an angle 60 degree. It come in between, this hydrogen come in between, this hydrogen come in between, and this hydrogen come in between these two hydrogen atoms. So eclipsed form of ethane, this is staggered form of ethane. Eclipsed form, here the bond pair of electrons are close to each other, there will be maximum interaction. This is your unstable form, but here they are farthest from each other, bond pair of electrons. This is the stable form. So in between them, you can rotate from 1 degree or 2 degree instead of 60 degree. You can get infinite other forms. All these forms are called skew or gauge forms. So conformational isomers arises due to free rotation around a carbon-carbon single bond. So I have given only two structures of ethane. That is, in one case the bond pair of electrons are close to each other, called eclipsed form. If you see this hydrogen, you can't see this one, and also other. If keeping the first carbon atom, front carbon atom fixed, if you rotate the second carbon atom through 60 degree, you can get another form, which is stable form, staggered form. In between them, there can be large number of other forms. If you rotate 1 degree, one form, 2 degree, 3 degree, many forms you can find. All those forms are called skew or gauge forms. So this is all about isomerism. Thank you.